These notes are over centripetal acceleration. So whenever you hear the word centripetal, it's just talking about uniform circular motion. And so in uniform circular motion, the radius and the magnitude of the instantaneous velocity, so in other words, speed, remains the same. Okay, and so as the object is orbiting around the or traveling the path of the circle, it is in fact accelerating though. Okay, so the velocity vector is always perpendicular to the radius. Okay, so if we had a circle, okay, and we had its radius, so here is my radius, the velocity or speed is always going to be perpendicular. So a 90-degree angle here to the radius, meaning that it is perpendicular. Okay, and so, like I said, because the object is constantly changing direction, even if the speed is constant, it is accelerating because it is changing direction. Okay, and so the acceleration is always directed towards the center of the circle. So it's known as center seeking. So that's what centripetal means. Okay, and so here is the magnitude of calculating the centripetal acceleration. So we denote this with a subscript c. So for centripetal acceleration, it is the velocity squared divided by the radius. Okay, and so to prove that it is center seeking, we can kind of look at a circular path where we have the same velocity going around. It has the same constant speed. The radius is going to stay the same, but if we change the time, so here after a certain time, okay, this is now its radius, and so the velocity, the second velocity would be here. And so what this is showing, in order to find the acceleration, remember it's change in velocity over time, change in time. Okay, so if we have our change in velocity, so v2 minus v1, so that's why this v1 is in the downward direction, because v1 was in the positive direction, so if we're subtracting, it would be in the opposite direction. Okay, and so our resulting change in velocity, delta v, would be this arrow. Okay, so it's kind of pointing inwards, but it's not completely to the center. Now, if we half that time, okay, so this was at like a 90-degree angle. If we half it to 45, okay, we have our v2 minus our v1, and then we get this delta v. Okay, so it's getting closer to being right towards the center. And then if we half that time so that we get a fourth of change in time, okay, so here we have it here. We have our v2 minus our v1, and my drawing is not perfect, but we should find that our delta v is pointed even more towards the center. So as delta t decreases, so change in time decreases, the delta v is directed more towards the center of the circle. So our instantaneous, and this is like a key thing here, if you don't draw out this whole thing, at least write down this last bit, the instantaneous acceleration is towards the center during any type of centripetal motion. So moving on, looking at the equation for the magnitude of centripetal acceleration. So they gave it to us here again. So AC equals our velocity squared divided by our radius. Okay, and so with higher accelerations, it would require higher speeds, and lower accelerations would produce lower speed of the actual object. So in the case of a car making a turn at a constant speed, if the turn radius is wide, meaning a large radius, then the acceleration is lower, okay? Compared to if there's a tight turn radius or a small radius, then the acceleration is higher. And you've probably felt this in a car. You can feel the change in direction more if someone takes a tight turn compared to when you're taking a curve in a road. Okay, you're not going to feel that change in direction as dramatically in a wide turn compared to a tight turn. Okay, and so in mathematically, we can say that centripetal acceleration is proportional to the square of speed. Okay, and then it's inversely proportional to the radius. Okay. And so for this first example, a young child sits on a merry-go-round 0.62 meters from the center. The child has a constant speed of 1.6 meters per second. Okay, first off, for part A, it says determine the direction of the velocity. Okay, and so like we had kind of drawn out in those examples with the circles, whenever we have centripetal motion, okay, so let me make my path. Remember that from our radius, our speed or velocity is always going to be perpendicular to the radius. So for part A, we can say that velocity is tangent to the circle, or you could say perpendicular to the radius. It kind of implies both the same thing, and the direction is always changing. Okay, for part B, determine the direction of the centripetal acceleration. Okay, we just kind of discussed this and proved this with the other three circles on the previous notes page. Okay, and so AC is directed towards the center. All right, and then for last one, calculate the magnitude of AC. Okay, remember that AC equals our V squared over R. So whenever I plug that in for part C, I get that AC equals, and then her velocity was 1.4. So I would square that, divided by our radius, which was already given in meters to us. So divided by 0.62, and we get that AC is 3.16 meters per second squared. So there is variations to the equation, the centripetal acceleration equation, right? And so just kind of as a review from physical science, if you did talk about this in physical science, there's two different terms that we can use to describe the motion in centripetal path, okay, and that is period and frequency. So period is the amount of time taken for one complete revolution, and it is represented with a capital T, and it is measured in seconds, okay? And then frequency is the number of revolutions per second, and it is represented with an F, and it's measured in hertz. So 1 hertz is 1 revolution per second, okay? And so just as a note, the relationship between period and frequency is that they are inversely proportionate, okay? So a period is equal to 1 over a frequency, or vice versa. Frequency equals 1 over period, okay? So if we begin with the equation for magnitude of centripetal acceleration that we were given earlier, okay, so AC equals V squared divided by R, okay? And we replace the speed with distance over time, okay? So we could plug this V into here, right? Because V is distance over time, so we could put those two variables in for V. Okay, the object will complete one revolution in the time span of one period. So one revolution is equivalent to the circumference of the circle. So we can change our delta t and delta d in terms of a circle. Okay, so for delta d, it's going to be equal to the circumference, which is 2 pi r. Okay, and then to go around, the time it takes to go to do the circumference of the circle is also equal to the period, so capital T. So we can plug that in as well. Okay, so if we were to plug in this delta T into here so that the period is going to go there, and then this delta D into here, we'll get that V equals, our delta D would be 2 pi r divided by our period. Okay, so I just plugged in these into this equation here. Okay, so now I have a new V. Now what I can do is I can take this here that's equal to V and plug it into this equation. So when I plug in this in for V, this is the equation that I get, and it's a little funky. So whenever we go through and simplify the equation, we are left with AC equals 4 pi squared R divided by period squared. Okay, and so we can use this equation when given period, which is capital T, okay, and the radius in order to find the centripetal acceleration. So if I was going to determine the rotational period of the child in example 1 using 2 different methods, okay, we should come up with the same answer, but let's go ahead and just check to make sure. So if I was going to be using speed and circumference, so speed equals distance divided by time, okay, and then I would plug in my distance to be the circumference. So in here, I'm going to change D equals 2 pi r, okay, and then I'm going to change my T, my delta T, to my period, okay, so I'm going to get V equals 2 pi r divided by T, okay. And so plugging in the information that I know that the velocity was 1.4 meters per second equals 2 pi, and then we knew the radius as well. It was 0.62 meters divided by T. If I solve for T, I get that my period is 2.78 seconds. Okay, so that's the time it takes to make one revolution. All right, for using the centripetal acceleration formula that we just used, or that we just calculated, we have AC equals 4 pi squared R divided by period squared. Okay, and then in the previous example, for example 1, we found AC. So AC was found to be 3.16 meters per second squared. Okay, so we'll plug all of our information in. So 3.16 equals 4 pi squared, and then our radius was 0.62, divided by T squared. Okay, and then so we'd have to get t by itself. So whenever we go through all the algebraic steps for that, we should find that t equals 2.78 seconds. Okay, so they are equal. So another version of the equation comes from the relationship between period and frequency. And remember, before I told you that for period and frequency, they are inversely related to each other. Okay, so if we have the previous equation, AC equals 4 pi squared r divided by period squared, okay, we can plug this in for t squared. So we would get AC equals 4 pi squared r divided by the inverse of frequency squared. So then whenever we simplify that equation, we get that AC equals 4 pi squared r f squared. Okay. Now, if you don't understand all of the different ways that I'm deriving these equations, it's not that big of a deal. I'm just showing you how you can manipulate the different equations to solve for different variables. But the key thing is that you just know how to use these three different equations. Okay, so this one. And when to use them. So for this one, you would use this whenever you're given, when you have two of the three different variables. Okay, so for this one, the three variables are centripetal acceleration, speed, and radius. For this one, the three variables are centripetal acceleration, radius, and period. And then for the last one, it's centripetal acceleration, radius, and frequency. Okay, so if you don't understand how I did all the derivatives, it's not that big a deal, like I said. You just need to know to use these three equations for solving for the different different variables. Okay, and then also noting that acceleration, centripetal acceleration, is always directed towards the center of the circle. Okay, so we are going to do this last example problem. So a record on a record player has a frequency of 74 revolutions per minute. So they told us a frequency, and it is in revolutions per minute. So we do need to convert that into revolutions per second to get it into hertz. Okay, so we would have for 1 minute there is 60 seconds, and so we'll get that it is equal to 1.23 repeating hertz. Okay, a fly sits 13 centimeters from the center of the record. So it did give it to us in centimeters. We want it in meters. So my radius will be 0.13 meters because there's 100 centimeters in 1 meter. Okay, and so it wants us to determine the centripetal acceleration and its rotational speed. Okay, so for finding the centripetal acceleration, we'll start with that. So we'll just call that part A, even though it didn't give it part A. They gave us the radius, they gave us the frequency, so we can use the equation AC equals 4 pi squared r f squared in order to solve for centripetal acceleration. So plugging in our information, and then solving, we will get that AC is equal to 7.81 meters per second squared. Or part 2, finding the rotational speed. So we'll just call it part B. Actually, let me use a different color. Part B. So for rotational speed, if you remember, the equation that has speed is the very first one. So AC equals V squared over R. Okay, we just calculated AC in the previous part. Okay, and they gave us the radius, so we just plug that information in. So we'll get 7.81 equals V squared divided by our radius, which is 0.13. And then when we solve for V, we get that it is 1.007 meters per second.